All right, this lecture is going to be on air temperature influences. We're going to look at 6 major factors that influence our local temperature. First thing we need to pay attention to is the human perception of temperature. That anything that influences the rate of heat loss from the body also influences the sensation of temperature. So we can see it like this. Let's say our body temperature, we know it's 98.6 degrees Fahrenheit. That if surrounding area is cooler, we would say, okay, well, 75 degrees is going to be, let's just say it's not warm. It's going to be kind of cool outside. And if it's 50 degrees, we're going to be losing more heat. Our heat flow, the rate of heat flow is going to be greater from us to the surrounding environment. So we would say it's much cooler, simply as a function of the rate of heat loss from the body that is influencing our sensation of temperature. But if the air is warmer than us, 100 degrees Fahrenheit, and heat flows from hotter to cooler, we'd say, well, yeah, it's quite hot. It's pretty hot outside. So when we apply this to the Earth, important factors that include temperature are going to be the air temperature itself, right? What we call our environment, the relative humidity, wind speed, and sunshine. So when I look at this, the rate of heat transfer, you feel colder when you give off or emit heat. You feel warm when the surrounding environment is warmer than you, that the net flow of heat would be from the environment to you. So let's look at this container of coffee. Coffee slowly cools by emitting heat via thermal radiation, what we call infrared radiation in the electromagnetic spectrum. But if this is a very slow flow, we would say that this is a very good insulator of that heat. It's keeping the heat in. It's still going to be losing some, but it's going to be slowed. So we would say that it's this coffee, this would be a good container. Well, you'll see that when we apply this here to the winter coat analogy, does a winter coat actually warm you? And you should know that no, it does not. A coat slows the thermal radiation your body gives off. It doesn't actually keep you warm or heat you in that context. It simply keeps your heat in and doesn't let it get out. So you heat up the air around you, or at least if this is a down coat, there's air spaces here. It heats that air up. It then insulates you from the surrounding environment, from the cold. In other words, it keeps the cold out, it keeps your warm in by you. So controls of temperature, when we apply this to the Earth, insulation is the single greatest factor. But then we also have geographic position. We could talk about the altitude or the elevation of a city. We can talk about the distribution of land and water. Is the city near a body of water, or is it inland? Is it influenced by air that's moving off of the land itself? We can talk cloud cover. We can talk albedo, right? Light and dark surfaces. So we can talk ocean currents, and we'll be addressing all of these. So atmospheric heating. The atmosphere is largely transparent to incoming solar radiation, right? Insolation. And we know the percentages. 50% is absorbed by the Earth's surface, and we know that 30% is reflected back and 20% is absorbed by the atmosphere in clouds. But we also have, once the sunlight reaches the Earth's surface, there's all kinds of different albedos, right? So we're talking about this overall percentage of the Earth has a broad range of variables just because they have different albedos. We could have dark and light materials, and they all kind of average out to changing local temperatures, right? When we talk about what's taking place when sunlight enters, we can say it reflects, right, based on albedo. We can say it gets scattered, and it can be absorbed. That the most visible radiation that reaches the surface, about 50% of it's absorbed. But that can be variable. That can depend on the light and the dark surfaces. So it's kind of an average value. So let's look at altitude or elevation. This is one of the controls of temperature. As altitude increases, the temperature decreases. A city at a higher elevation will have both less pressure or lower air pressure and a lower average temperature than a city of equal latitude near sea level. So as I rise in the air, just like we know from our troposphere, it gets cooler. So cities at elevation are going to be cooler. So this is showing you not only pressure in millibars, but our temperature in degrees Celsius. So altitude, directly related to, as altitude increases, right, our temperature is directly related to elevation. The temperature decreases. So altitude and temperature are inversely related. Distribution of land and water. 2 coastal cities can vary significantly based on how prevailing winds move air. Eureka, California, on the west coast, is tremendously influenced by the Pacific Ocean, whereas New York City, still a coastal city, but is influenced by heat moved by winds over the land. You have to understand that air is coming from the southwest, so Eureka is going to be receiving air that's blowing off the oceans directly, whereas New York City is going to be getting air that's blowing directly off of North America, or excuse me, the United States. So it's getting air that's blowing off of the land. Both are coastal cities, but they have a wide temperature range in comparison to one another. New York City and Eureka is going to have a much more stable temperature differential, right? And New York City is going to be more influenced by the land, right? Remember, specific heat. Specific heat of water is going to be much more stable. Specific heat of land is going to be much more unstable. And that's what we're looking at here. And that's what the graph is showing us. Cloud cover. Examples of cloud feedback. High clouds trap more heat. Low clouds reflect more sunlight. Clouds have the ability to both reflect sunlight and absorb sunlight. So high clouds absorb insolation and emit infrared energy, much like that of the Earth's surface, while low clouds have a tendency of reflecting sunlight. Clouds can also have a warming effect. Clouds can trap warmth and serve as kind of a blanket. The coldest days are typically clear, dry, and cloud-free, whereas you can actually get warmer days, particularly in humidity, high temperature, high humidity, on days in which where you have cloud cover. Albedo. Light and dark surfaces respond differently to sunlight energy. So it's a combination of all the albedos on Earth's surface that lead to the imbalance of heating. This is very key. Make sure you get this in your notes. The imbalance of heat is what generates wind. So we're going to be talking about how the changes in temperatures are going to lead to changes in pressures, which are then going to drive wind. Well, let's make sure we identify ocean currents. The oceans are the Earth's thermostat. They regulate its temperature. Surface currents shown below illustrate how warm currents flow poleward, right, toward the poles, while cold currents flow towards the equator. And you can see that the warm currents, the red arrows, are moving away from the equator. Warmth is, in general, absorbed greatest amount at the equatorial oceans. Those ocean currents move away, and cold currents return. And they're really just circulating the heat from the equator, and they're moving it toward the poles, and they're moving the cold from the poles towards the equator. It's a really, really cool system. Isotherms. These are lines of connecting equal temperatures. An isotherm allows a meteorologist to find areas of equal temperatures. The lines connect dots of equal temperature in order to make predictions of future temperatures as air moves across a landmass or a continent or even an ocean. Often they are color-coded. If we can kind of convert this into a color map, we would see that this would be your colored isotherm map. But these lines are just connecting lines of equal temperature. And here are your numbers. Here's your scale here. 20, 30, 40, 50. You've got larger numbers down here. Here's 80, etc. So connecting lines of equal temperatures. So here's a world mean temperatures for June. So land and water heat up differently. We can view this by looking at isotherms. Then they have different specific heat. The lack of straight lines is generally due to ocean currents. Ocean water, higher specific heat, influences local temperatures dramatically. The isotherms in the picture in June are not straight, except near the South Pole, down here. Think about where the sun is located. It's located up here near the Tropic of Cancer. So when I compare this, you have to make sure you pay attention to what's going on. Where the sun is most directly overhead, the land is going to heat up much more dramatically. The water is going to heat up differently. So ocean currents are going to kind of bend and tweak these isotherms. Well, in January, during the Northern Hemisphere's winter, we would see that these isotherms are just much more differently displayed. Why does the Southern Hemisphere heat up much differently than the Northern Hemisphere? Well, it's a difference in land and water. Also notice how nearly horizontal the isotherms are. When the sun is more closely directly overhead the Tropic of Capricorn, we just see a different isotherm pattern. Now I'm going to go back and forth. I want you to see how the isotherms differ. And I labeled in the Tropic of Cancer and Tropic of Capricorn just to give you a little perspective here. I'm going to go back and forth. And notice how the isotherms kind of bounce back and forth during a calendar year. They're simply reflecting the insolation that's acting on different parts of the land masses. So that concludes this particular lecture.